Chapter 5 Partial Differential Equation.
From the equation given, we know that we have to solve one-dimensional heat equation. The general solution that is given is, and two boundaries conditions that are given from the question are. So let's solve this question. For the first step, we must use method of separation of variable. This method is used to separate PDE into two ODE for the variable x and t as the general solution, which is, then sub the u value into the heat equation. For the left hand side, we need to differentiate with respect to t, while the right hand side with respect to x. Then, gather all variables of t on the left hand side and variables of x on the right hand side. After that, we introduce separation constant negative lambda into the equation. Now, we can solve two separate ODE in terms of t and x by equalizing both equations with negative lambda. Rearrange both equations until they are equals to 0. Next, make sure that our product solution satisfies the boundary conditions. So, rewrite the boundary conditions so they associate with only one variable. How to derive the boundary? We need to substitute value of x, which are L and negative L, into the general solution for both boundary conditions. We need to decide which variable will equal to 0. Hence, to avoid trivial solution, we choose V negative L and VL equals to 0. Why choosing GT equals to 0 will give us trivial solution? Well, this is because t is unknown and the value of t can be any number, while v negative L and VL are already a specific value, which are negative L and L. So this situation will give an appropriate solution. That's why we choose v negative L and VL equals to 0.
For the second step, we need to find value of GT. To find GT, we can use the previous equation. Rearrange the equation with variable g for the left hand side and for the variable k at the right hand side. After that, we need to integrate both sides until we get the value of GT. We can leave the constant here and combine it later with constant of Vx. For the third step, we need to find Vx. We have three cases with different conditions, each which are lambda less than 0, lambda equal to 0, and lambda more than 0. We need to test each case by using previous equation that we separate to get value of Vx. For the first case, lambda less than 0, the general equation is. Next, substitute the first boundary condition into the general equation. Since the first case condition is lambda less than 0, then we cannot equal L set negative lambda to 0. So, we will get C2 equal to 0. Then, repeat the step by replacing the first boundary condition with the second boundary condition. We will get the value of C1 equal to 0. For this case, there is no solution. For the second case, lambda equal to 0, the general equation is C1 plus C2x. Substitute the value of first boundary equation into the general equation. Applying the first boundary condition gives C2 equal to 0. C1 will also equal to 0, and this will regard the second boundary condition as trivial solution. Hence, solution does not exist for this case.
Let's continue with the last case, lambda more than 0.
This is the general solution. Substitute the first boundary condition negative L and L from one equation by make equation 1 equal to equation 2. Since cos negative x is equal to cos x and sin negative x is equal to negative sin x, rearranging the equation will give us, then we will get 2c2 sin L set lambda equal to 0, which is also equal to Vx. We know sin n pi equal to 0, hence n pi equal to L set lambda. Rearranging lambda as the subject will give us n pi over L squared. Next, substitute the value of lambda into Vx. We can ignore the constant because we can combine the constant at the final answer with the constant of Gx. Next, repeat the exact same step with second boundary condition until we get. By using the lambda we got previously, sub the lambda value into the equation. Since lambda equal to n pi over L squared, hence lambda more than 0. So Vx equal to sin set lambda x for first boundary condition, and Vx equal to cos set lambda x for second boundary condition. Finally, we get Vx equal to sin n pi x over L. We get Vx equal to cos n pi x over L. Proceeding to the fourth step, combine Vx and Gt into general solution. Gt originally equals to, by substituting the value of lambda, we will get Gt equal to. After combining Vx and Gt, we will get, for the cosine function, we replace constant with an, while for the sine function, we replace constant with bn. We can rewrite the general solution into Fourier series solution. Then we will get the final answer as with
Santuy.
That's all. Thank you.